This chapter will discuss about regularization techniques for regression problem. There are several kinds of regularization. We focus on two of them. One of them is L1. The other one is L2. This is the the L1 norm regularization. These two regularization techniques have been widely used in many regression problems. We start from the basic, and then by the end of this chapter, we will give a more generalized problem in terms of sparse estimation. So today, I think we can cover a little bit about overview and the L2. The overview. So if we focus on regression problem and probably take a look at the simplest one, that is the least square. The problem statement is of course to fit the residual norm, the two norm, the residual, and then if we solve the least square, you would see that typically the solutions beta are non-zero. Okay, sometimes I use the term dense. All right, so it's a dense vector. We also have results that in the scenario that P is much bigger than N. P is the number of variables, the number of predictors, and big N is the number of samples. Of course, when P is much bigger than N, your regressor matrix is, how does it look like? Tall, fat, or square? True.
Can you repeat that?
In the scenario that you have more variables, have much more variable than samples. The matrix, the regression matrix is, how does it look like? The dimension, square, tall, or fat?
Tall, Ajahn.
Tall.
Fat.
Fat. All right. The regressor matrix is fat. Okay. And of course, when you solve, you would know that if you reduce, if you minimize the residual between x and y and x beta, that residual vector becomes a fat, right? Fat vector. It's not a fat vector, sorry. So it's I should have said that when x is fat, right? So the estimate, the beta hat, is typically not unique because you have so much freedom, so much choices on beta to make these guys match with y exactly, right? So it's a fat system. When that problems, like when we have observed these character from the least square solution, especially in the last observation, that this is the scenario that is often found in the high dimensional setting, right? When we have like much more variable than the number of samples. So in this with this situation, okay, people have come up with a way to regulate the solution. Okay. So what we mean by regulate is that we regularize the estimation process by solving another problem. And another, the thing that we twist in the estimation process is, okay, here I give an example that now we restrict the solution beta to satisfy these conditions. With this condition in the yellow box, it says that the sum of absolute values of all the entries in beta must be less than a scalar t. And this scalar t, of course, because this is a sum of absolute value, this yellow condition is only meaningful when t is non-negative, right? Because the sum of absolute value must be non-negative. And by the notation of vector norm, this sum of beta j is basically the one norm of beta. Okay, so the meaning is that you don't have a freedom on choosing beta, but then you have the constraint that the one norm of beta should be limited by a scalar t. So you kind of have some budget on the norm of the vector beta. Okay, and then okay, with this we're gonna show you later that using L1 norm here, and when t is small enough, the behavior of beta is that it's going to turn out to be a sparse solution. And sparse solution is favorable in many situations. For example, because we know that when you have the linear regression model, right? If sum of the beta is 0, all right, so of course immediately you would interpret that the corresponding predictor is not significant. It is not important. So in many applications where the set of predictors like contain so many variables like gene expressions of cancer data, okay, like if you have like 1,000 genes, right? And which one is significant? So in this high dimensional setting is you know, it's going to be applicable to this kind of regularization process. So when we solve regularization problem, okay, it's going to turn out it's going to have these character in the solutions that some of the predictors will be 0. Only like part of them. So only part of them would be would give the user to interpret the result that okay, just these group of genes are significant to explain, right? To explain the cancer, to explain the response variable according to the cancer. Okay. In another application, let me. Oh, sorry. I think we have another. No. Okay. Okay. This is what version of this? Sorry. Oh, okay. I should have used another version. Sorry. Dun, dun, dun. So in another application that I would like to show is about reconstruction. With this, so people have solved, transformed, find a wavelet transform, right? And then okay, here. Okay, so another example is about image reconstruction by wavelet representation. So the wavelet representation would be something like a basis expansion that you have the coefficient, right, multiply with the basis function, which is the wavelet function, coefficient k and the function k. So the plot in the middle here is wavelet coefficients, all right. The thing is, not all the wavelet coefficients are necessary to explain significant components of an image. Okay, if we in this type of regularization, if we zero out some wavelet coefficients, for example, in the initial model, so it would be like coefficient 1 times wavelet function 1. You know, the wavelet function, they have parameter, right? They have translation parameter, they have dilation parameter. So suppose fk is one of them, all right? And a lot of them, cn, the coefficient, let's say, CP, FP. So if you just zero out just some of them, okay, and then keep the significant ones. You will see that after we reconstruct by using only non-significant wavelet coefficient, if you look at the pictures, I mean visually, you probably don't see any significant differences. So it's hard to notice that, oh, these two, I mean, this is the reconstructed image and this is the original one. So with this meaning, it means that probably finding a sparse solution, which means only important predictors in the model would be enough in order to explain the response Y. Okay, so this idea, again, if we take a look at this in two aspects, all right, is more about how are you going to trade off between prediction accuracy and interpretation of your model. Okay. Of course, if you include all the predictors, right, the prediction would be good. But I mean, having 100 predictors and having like 1,000 predictors, if the prediction accuracy are very similar, why would you pick a big model? Again, and yet this is a trade-off between bias and variance. Okay, so if you shrink some of the beta in the big model, and it turns out into having only 100 variables, all right, it means that your simpler model probably has some more bias, but what you gain is that it has lower variance. Okay. Okay. In terms of interpretation, non-zero predictor would be the subset of predictor that would have strongest effects on the regression model. Okay. Okay, now we what I have presented is kind of a usefulness of L1 regularization. Now we're gonna talk to the first one that is simpler to understand. This is L2 regularization least square. The problem setting, the problem statement is that in addition to the conventional least square cost objective, we add penalty term that is a 2 norm of beta square. All right, and we have these coefficient gamma. All right, so gamma is a non-zero and non-negative parameter designed and given by the user. When we have these two objectives, all right, so we keep in mind that when we optimize, in terms of optimization, when we optimize some of the two cost objective, right? It basically means that you want to minimize the sum of the two, all right? But when you have an option to play with the weight, with the penalty weight between F and G, so the role of gamma here is to put more attention to like you can decide to put more or less attention to G. So if gamma is big, it means that you tend to penalize G more. You care more about G. G should be minimized with a heavier weight in relative to F. Okay, so which means if we kind of explain that in this scenario, so the meaning of minimize the norm of beta square is of course has a meaning of you prefer the regression coefficient that has small norm. And why do we want beta to have a small norm? Again, it comes from the you know, from the usage of these regression coefficients that remember that when we estimate a model, we get a beta hat. So in the process of estimating the value of y, what you're gonna do is for the new data set, right? You're gonna have a new regressor matrix X. And then if I have to predict y, I would multiply this x with the beta hat. Okay. So a lot of times the regressor matrix comes from like collecting the predictors values, right? From in the world of engineering, we observe, we sense these values through a sensor. So typically these values, right, the measurement of all the variables involved contain some uncertainty, some randomness, something corrupted by noise through an equipment. So it most of the time we can say that these parameters may contain some uncertainty. So when I have this notation, it basically means some nominal value and some uncertainty. When you have this, right, when you would see that some undesirable perturbation on the regressor matrix X would be also amplified or suppressed by beta hat. That means if your beta hat is big, and when your regressor matrix has some uncertainty, you're gonna have more uncertainty in y hat, which means the prediction of y, the point estimate of y, would become even more unreliable if beta hat is big. So having a small norm on beta hat can alleviate these issues, because if beta hat has smaller norm, right? If it has smaller norm, even if your data has some perturbation, that perturbation in the prediction of y would be less. Okay, so this is the motivation of why do we have small norm in the regression coefficients. Okay, the L2 regularization just pick the choice of two norm in order to explain the length, the size, the magnitude of regression coefficient. Okay, with this regularization technique, it has a name. It's called ridge regression or Tikhonov regularized least squares. And the role of gamma here, it would control a trade-off between fitting error and the size of beta. Sorry. Okay, so when gamma is big, what happened is the norm of beta square would be big or small, Thirawat?
Small.
Would be small, and the prediction error in relative should be
Should be smaller.
Not smaller, because you minimize these two terms at the same time. So what I'm sketching here is, I mean, everything is with the relative to the other. So when I say gamma is big, right, and we say the norm beta is smaller, that's what I mean is in relative to the sum. Okay, so the prediction error would be bigger, because you put so much weight on the other term. Okay, if
okay.
gamma is less, Thirawat, gamma is beta square is
bigger.
Then the prediction error square is
Smaller.
So if gamma is less and less, of course, it means that more focus has been paid attention to on the model quality, the prediction error, right? And then you care less about the small norm of beta. So you have, again, this is again a trade-off between model quality and model complexity, because when beta is small in the norm sense, right, when the norm is small, of course, as you know, the norm of the vector, they look at the each components, right? So I mean, eventually, if the norm is small enough, I mean, some of the entries will be very small, will be close to 0. And that further means that the model complexity is less and less. All right. So having this regularization is yet again come to the trade-off between what model complexity and model quality. If you look at this estimation mathematically, with it's unconstrained, but unconstrained problem, we have cost objective. So we can solve it, and because this is a norm square, we can solve it the same way we solve the least square, which means we can take the gradient. All right, I call this f. I take the gradient with respect to beta, and then the gradient would be x transpose y minus x beta. Okay, and then with the minus sign x because of the chain rule, and plus gamma beta. Okay, so this is the derivative of the second term. And then I can group the variable, that is x transpose x, right, plus gamma I times beta. And of course, now what I'm gonna do on the gradient is I set it to 0, because that is the optimality condition for minimizing f. So if I if I move this term to the other side of the equation, all right, that is x transpose y. So you see that this equation is very similar to the normal equation of the least square, but you have additional term that comes from the L2 regularization. A good thing of having this L2 regularization is that unlike the least square, that you need to rely on the invertibility of x transpose x. Mathematically, this matrix is always invertible as long as gamma is positive. Okay, this is one fact. This is one fact, all right? So I mean, basically this fact is rely on the fact that if any metric is positive semi-definite and some gamma is positive, all right, then B plus gamma I is always positive definite, which further means that B plus gamma I is invertible. Okay, so this is some elementary fact in linear algebra. Then, which means that from this normal equation, we can have a closed form solution in the rich solution, just the same way we have for least square. Okay, there's an important result that this rich solution can be interpreted as a maximum a posteriori estimation with the log prior of the Gaussian. All right, I have some short video on this type of estimation. You can watch it as well. So with the meaning is that the meaning about map estimation is that in map we also have assumption of the variable of the estimator that it also random. So when it is also random, we have some prior knowledge. And in the context of our L2, we have a prior knowledge that beta is actually Gaussian distributed with some, with some mean, some variance. This is something as is a prior knowledge about your coefficient. And given that you have prior information, this is the best solution I can give according to the principle with the map. Okay. Okay, here we have some results, MSE of the ridge regression. Please refer again. We have two names, all right, Tikhonov or Rich. In this plot, in this slide, so probably I use different notations. Here I use gamma as a penalty parameter of the L2 norm. But then, sorry, I use lambda here, but please remind that it means the same thing. Okay. Okay. So basically, lambda is penalty parameter. Okay, that multiply with the regularization term. Sometimes it's called regularization parameter. Okay. Well, this plot we plot what? We plot MSE versus regularization parameter lambda, and then we have test, right? And then we have variant and square bias. As we see, as lambda increases, as we see before, when lambda increases, the norm beta is small, right? When beta is small, so what do we have in the square bias? Square bias is this term. Okay. What happened, Panat?
Bias increase, right?
The bias is increased because remember that of course the beta that give the minimum mean square error would be the one that minimize the least square. But now the solution beta come from solving the minimizing the two terms, right? So this beta regularization, okay, is no longer optimal in the original least square problem. Okay.
So it is not blue anymore, like.
This is not what?
Not blue property of linear regression.
The blue property, the best linear unbiased. No. All right. Okay. I hope everyone follow this, right? So you see, I need to change. Okay. So you're gonna see that the square bias is increased as lambda increases. At the same time, when lambda increases, the norm of beta is small. And as I said before, that's gonna reduce, you're gonna see a reduction in the variance. Okay. If we plot the test MSE, okay, test MSE, which means that you solve the regularized, you have solved for beta hat, regularized beta hat, and then you evaluate. So you evaluate with the y new, the new data, the new regressor, and you multiply with this regularized solution. And then you compute the norm square divided by samples, that the test MSE. We can see kind of something as a recommended value of penalty parameter, you know, that achieve the lowest test MSE. Okay. And then on the plot on the right hand side have the same interpretation, but with a difference in the x-axis interpretation. The x-axis is actually the norm of regularization divided by the norm of the least square solution. So so as lambda increase, the norm of the regularization would be small, right? So the the x-axis of the right-hand side of the right graph would be switch. So small norm in the regularized solution would be when lambda is big, and here is lambda is small. Okay, so that's why the trend of the variance and the square bias of the right hand side would be the other way around from the left hand side. Okay. All right. That's some results from the regression. The regression also have a similar form that people have used in practice. So we can move the L2-regularization as a constraint. So instead of having this formulation, okay, we can also put the optimization in this way. 2 norm of beta square is less than some number. Okay. And if you use this form, you have to specify the upper bound of the 2 norm of beta. You have to define this t. Okay. The previous formulation is called the Lagrangian form of this problem. Okay, so this is from optimization point of view. Okay. There's going to be some corresponding, so these gamma and these t, they form a pair. If you use this formulation with this value of t, it's going to be equivalent to solving this formulation with a value of gamma. Okay, so it's just two forms, all right? But t and gamma are not the same values. There's some practical issues, some concerns about implementing the regression. Typically, you have seen that in the typical linear regression, people may include, all right, a lot of time they include the intercept term, right? And then, but when it comes to the L2 regularization, because with the meaning and everything for the model to be interpreted meaningful, you shouldn't regularize or penalize on the intercept term. Okay, so that so when you have the intercept term, this term should be the norm of beta 1, beta 2, to beta p. Okay. And the solution can still be derived in the same way, but you have to be careful when you derive the solution, because now the the term beta 0 should not be included in this norm. Okay. We have one fact that that is no longer true. Okay. So when we have the linear regression model, okay, if we scale the predictors in the linear regression, when we scale the predictor by a factor of alpha here, okay, where we can represent it as a vector matrix product as x times d, where d is the diagonal, right? If you have, so this is a good exercise, right? So when I have a regressor matrix X, okay, and I solve for regression coefficient beta, and with another regression model where I scale the predictors, sometimes I scale it according to the unit. So let the regressor matrix that is scaled, let it be X tilde. In that case, if I solve the regression coefficient, that's going to be a relation between, so I use this notation. It doesn't mean that they are the same, but there's a relationship. It's actually affine. Okay. It's a good exercise how they are related. Okay. For example, I think you can think of this now. Okay. So in the next model, okay, I'm gonna start with the non. I'm gonna get rid of the intercept term. For example, if my x1 tilde is a predictor that is scaled by a factor of, if I scale down by a factor of 110, what would be the relation between beta 1 tilde and beta 1. Napat.
Beta 1 tilde is 10 times greater than the beta 1.
Should be beta 1 tilde should be 10 times beta 1, right? Because I mean, right? Can everyone see this? Is it clear? Because this variable has been scaled down, right? Scaled down by a factor of 110. In order for this term to explain the same amount of y, right? So beta 1 tilde should be compensated by a factor of 10. So that's what I mean by scaling down, or I mean by scaling the input or the predictors. There's going to be a relation between regression coefficients of the two models. Okay, and you can write it in the closed form. That property is no longer hold for the ridge regression. Okay, because we can show, okay, that's gonna be a good exercise, because we can show that the ridge regression, the ridge solution would also depend on both D, the scaling coefficients, and the penalty parameter. Okay. So typically when people perform this regression model and with the regularization, so a lot of time they standardize the the sensor matrix, the regressor matrix. What we mean by standardized is the following. You have P columns, right? Can someone suggest this? Maybe Panat, you already know. What do we mean by standardized?
We weight with something.
Yes, but the common one is of course to remove the mean for each column. Right? Each column means each variable, each predictor. So first we remove the mean, okay, and then of course everyone should know that remove or not remove the mean, they have the same variance, right? So then you compute the the variance of the first variable, the second column, right? And then first you remove the mean, right? Becomes tilde, and then we standardize it in the way that each column has a unit variance. So each column would be normalized by, should be normalized by what? Theta what?
Square root of the variance.
Yes, square root of the variance. So you normalize it. So that's a expression that I have here. Okay. So that's how practical implementation of the regularization problem. So standardize the variable first. Okay. So that's a two norm regularization.